Hello. Good morning, madam. Please unmute.
Yeah. Ah. So can you hear me now?
Yes, yes, yes.
Yeah.
So, good morning to everybody. Today we will start with the lecture of Professor Smita Bedkar, madam. So, she will continue from where she left yesterday. So, so should we wait for 2 3 minutes, madam? Because only 20 people have joined. Or we can start.
As you wish, maybe we can start at 11:05.
Yes, 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 yes,
Okay?
yes.
Yeah. Am I audible?
Yes,
And the presentation, is it seen on the?
Yes, ma'am.
Yes,
Yeah.
ma'am.
So can we start now?
Yes,
Yes, ma'am.
yes, yes.
Huh?
Yes, 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 please start.
Yeah. So let me begin where I stopped yesterday. Good morning, everyone, and we are going to look at the verse 128 and 129 of Shredhi Vyavhar today. Okay. Actually, this Shredhi Vyavhar has this two verses, 128 and 129, the last two, which are devoted to a very different topic, that is this binary strings. Okay. And if you look at this topic in our textbooks today, it really comes close to what is permutations and combinations. And that's why I have put it in this lecture. Those last two verses, they are anyway independent of whatever had been done in previous 16 verses. Okay. So we come to this topic of what is known as binary strings in today's world. So, what are these binary strings? We will briefly look at. They are sequences of zeros and ones of certain length. That means there are certain number of zeros and ones in them. Uh, and they are extremely important in computer mathematics. As we know, in computers, we are working with binary numbers. Surprisingly, these binary strings, they appear in Leelavati. Okay, the terminology is entirely different. It is entirely different, and we have to understand this terminology a little bit. This terminology is of poetry. Okay. So, what is this terminology in poetry means? That is what we will see today. So, this in there is what is called as vrutta. Vrutta is something which has four charans, and these charans have letters. Okay, depending on the type of the letter, the charan is uh, these letters have two types, that is Lagu and Guru. Okay, and these charans have this Lagu and Guru arrangement of Lagu and Guru letters, and depending on the type of charan, the vruttas are classified. Okay, so the vrutta consists of four charans. Charan consists of letters. Letters are of the type Lagu and Guru. And then these charans make vrutta, and the type of charan that makes type of vrutta. So the so we call it samavrutta if all the four charans have the same. Uh, okay, there is a typo here. All the four charans have the same pattern of Lagu and Guru. Okay. Samavrutta means all the four charans have the same pattern of Lagu and Guru. Ardha Samavrutta means first and third charan have the same pattern of Lagu and Guru. And second and fourth charan, they have the same pattern. So Ardha Samavrutta means first and third is following one pattern, second and fourth is following another pattern. And Vishamavritta means each charan has different pattern. Okay, each charan has different pattern. So this using this our counting principle, if a charan has n letters, then what will happen? The number of Samavritta will be 2 raised to n, because the charan can be written in 2 raised to n different ways. Charan can be written in 2 raised to n different ways, and Samavritta means all the four charans are the same. So there are these 2 raised to n ways, 2 raised to n ways in which the pattern of Lagu and Guru can be written in a charan of n letters. So this number of samavritta is equal to 2 raised to n. While the number of ardha samavritta, what we have to do is that first and third charan has the same pattern and second and fourth has the same pattern. So for first and third charan, we have 2 raised to n numbers, while for second and fourth, we have another 2 raised to n. So their multiplication gives us the number of different arrangements 2 raised to n into 2 raised to n. But we have to subtract the number of samavritta from this arrangement. Okay, we have to subtract the number of samavritta from this arrangement. So we are subtracting 2 raised to n from this. So number of ardha samavritta turns out to be 2 raised to n square in 2 raised to 2n, in fact 2 raised to n whole thing square, 2 raised to 2n minus 2 raised to n. And then Vishamavritta. Vishamavritta has every charan of different arrangement. So the number of total arrangements is 2 raised to n into 2 raised to n. This is 4 times. Then we are subtracting samavritta from it. So we are subtracting 2 raised to n. And then we are also subtracting the number of ardha samavritta. So that is 2 raised to n whole thing square. It's not 2n square. So from 2 raised to 4n, the number of samavritta and ardha samavritta are subtracted, and the number of vishamavritta is 2 raised to 4n into 2 raised to minus 2 raised to 2n. Okay, minus 2 raised to 2n. So the question is that all this mathematics is fine. We'll take one example. So when we are having this Anushtup Chanda. Okay, Anushtup Chanda is again the term from poetry. And this Anushtup Chanda has 8, each charan has 8 letters. So the number of samavritta are going to be 2 raised to 8, 256. Number of ardha samavritta, they will be 2 raised to 8 into 2 raised to 8 raised to 2 minus 2 raised to 8. So that is what is this number. And the number of vishamavritta, that will be 2 raised to 8 raised to 4 minus 2 raised to 8 raised to 2. So this is going to be this large number. So this is an example of whatever that counting of samavritta, ardha samavritta and vishamavritta. Okay. So this is an example of this, and this Anushtup Chanda, Vritta, Charan, everything comes in the verses in the poetry. Now this, yeah, yeah, yeah. No, I'm not getting the question.
Please continue, madam. Please continue.
In this, so the question is that when we are talking about this Chanda, Vritta, Charan and all that, where do we count all these things? Is there any hardcore mathematics in poetry? And if we map this Laghu and Guru to 0 and 1, what we are getting is the number of binary strings. Okay, binary strings of certain type. So what are these? That we have the string length as 4n. The string has 4 parts of length n. And samavritta means all 4 parts are alike. Ardha samavritta means alternate parts are alike. And vishamavritta means no 2 parts are alike. Okay, no 2 parts match each other. So we are talking about binary strings, and Bhaskaracharya was well versed with these binary strings. where exactly these binary strings were applied, it's not really clear. The application part is not at all clear, and it is not, in fact, even after studying Bijaganit, it was not clear where exactly these binary strings are used. Maybe this requires more deep exploration into all this mathematics, that where exactly binary strings were used. And these are the last two verses of Shredi Vyavhar, and they are independent of remaining 16 verses. If you look at our textbooks, they go well with the next topic, that is this Ganit Pash or Anka Pash, what is called. And that's why I had put it in this lecture. Now, this Ganit Pash or Anka Pash, it is the last chapter of Leelavati. Okay, it has got just 8 verses. It has got just 8 verses, but as we will see at the end, that Bhaskaracharya calls it the toughest part of Leelavati. Okay, Bhaskaracharya himself calls it the toughest part of Leelavati. So, what is done in this 8 verses? Yeah. So this verse 250, it describes the computation of n factorial and the permutation in PR. Okay. It describes n factorial first and in the permutation. And the examples given here are mostly numbers. Mostly numbers, I will say, because we are going to look at a peculiar example also that comes with some religious context. So here, what does Bhaskaracharya do is that he not only asks for the number of numbers with certain digits, but also wants the sum of the numbers. I think we don't do it in the textbooks nowadays, sum of such numbers. And he tries to work out a formula for that, which of course works. So these examples, first two examples are the simple sets of digits 2 and 8 and 3 and 8 and 9. And the question is that how many numbers you can form out of these digits and what is the sum of those numbers. The next set which Bhaskaracharya had chosen is 2, 3 up to 9. There are these 8 digits. Okay. And even for these 8 digits, Bhaskaracharya wants quick answer for the addition of the numbers. Bhaskaracharya wants quick answer for the addition of the numbers. Okay. So you have to not only state how many numbers can be formed out of 8 digits, which we know very well that it is 8 factorial, but you also want to sum the numbers. How do we sum the numbers? So the formula given is that if you take n to be number of digits and d to be sum of digits, d to be sum of digits into n minus 1 factorial, then this addition of n factorial numbers is given as d into 10 raised to n minus 10 raised to n minus 1 upon 10 minus 1. Okay, d is the sum of the digits and n minus 1 factorial is the multiplying factor for this. And this big number will give you the sum of the digits. So let's see how exactly this number came. Okay, so we have to add n factorial numbers. So let's start by adding unit places of n factorial numbers. Since these numbers are made up of n digits, okay, each digit will be repeated n factorial upon n number of times. Each digit occurs with equal probability. So each digit will be repeated n factorial upon n number of times, that is n minus 1 factorial number of times. Okay, so in this n factorial numbers, there are n digits occurring. Each digit is occurring with the frequency n minus 1 factorial. So if we have this d1, d2, dn denoting the digits, if we have d1, d2, dn denoting the digits, then if we sum them d1, d2, dn, each of these digits is going to come n minus 1 factorial times. So if we add the unit places, the number which we get is n minus 1 factorial into d1 plus d2 plus dn. So what we do, we call this d1 plus d2 plus dn is equal to d. And then if we have to take sum of all numbers, then what we have to do is that we have to add units places, we have to add tens places, 10 square places, so on, our elementary school mathematics. So when we are adding these numbers, what happens? This every place when we add, the sum is going to be d into n minus 1 factorial. So the number, if we add, it becomes d into n minus 1 factorial plus 10 into d into n minus 1 factorial plus so on. We keep on doing this till 10 raised to n into d into n minus 1 factorial. So if we sum this thing geometrically, this is what is the number. This is the geometric progression, and as we had seen in the last lecture, this is what is the number of numbers. This is what is the sum of numbers. Okay. So this formula is given along with the number of how many numbers we can form. Along with that, this formula is given. We will just see. Okay. Yeah. So we will see this example that if we have this digits 3, 8 and 9, okay, then the sum of the digits is 20 and we are forming 3-digit numbers out of this. So our d is 20, n minus 1 factorial is 2 factorial, and we have 10 raised to 3 minus 1 upon 10 minus 1. So you know what is the number we have. We have 4,440 as the sum of the numbers. And how many numbers they are? They are 3 factorial, that is 6 numbers. So of these 6 numbers, the sum is 4,440. So Bhaskaracharya's problem does not become complete without finding this sum. Number of numbers, we had been always doing that in our problems and everything, but there is this sum which is different. Okay. So if we have to repeat this for, yeah. The set which is 2 to 9, then D will be 44, N will be 8, and the sum will be 44 into 7 factorial into 10 raised to 8 minus 1 upon 10 minus 1. What is the number? That is not important, but it is going to be a huge number. And what is most important, that playing with very large numbers without calculators or computers at disposal was the game of those days. The people who did mathematics in those days could always play with large numbers. Okay, maybe because of our gadgets, that is first the calculators and then the computers, we are losing this ability of manipulating the numbers fast. But people doing mathematics in those days must have been extremely good at doing these operations on large numbers. Now, this example is followed by something from religion. Okay, something from religion. So, this um, Lord Vishnu and Lord Shiva, they have different number of ayudha. Ayudha, that is for Vishnu, it is Kong, disc, mace, and lotus, or Shankha, Chakra, Gada, and Padma. And for um, Lord Shiva, there are 10 ayudha. So, this question is that in how many different ways this can be depicted in a statue of Lord Vishnu. Lord Vishnu has four arms, carries four ayudh, and so this four ayudh can be put in four arms of Vishnu in a statue in four factorial ways. Okay, in four factorial ways. And if you try to do this for Lord Shiva, there are 10 factorial ways because Lord Shiva is supposed to have 10 hands. Okay. Now, this 24 names of Lord Vishnu, surprisingly, they appear in a daily ritual. Okay, in a daily ritual, there are 24 names of Lord Vishnu, and each of this name is supposed to be with a unique combination of ayudh. Okay, these 24 names with 24 names with 4 ayudh in 4 hands, different combination that makes it 4 factorial, that is 24 different combination, and each name of Vishnu has a unique combination out of this 24. So the religion in our religious text, some things appear, the ritual stays, but the mathematics behind it, no one really understands. In fact, it will be good to extract mathematics from some such peculiar things. So, for Lord Shiva, I think this is 10 factorial, so I don't think Shiva's 10 factorial names were there. There are several, but maybe not 10 factorial, and not the listing of them. So then what is done next in Leelavati? Is about sets of digits where there are repeated digits and sum of such numbers. So as we know that the formula will change when we have repeated digits, and the change in the formula in this will be in this factor, which is the sum of the digits. Okay. So what the next thing which we deal with, of course, we know these results as we do them in our maths textbooks, that if you have digits say 33577, then what will be the number of numbers? So obviously you can find it out from this formula, but how to find the sum of these numbers? That is the question. How to find the sum of these numbers? That is the question. So the sum of these numbers, now we apply different logic that there are these 30 numbers and this 5 out of these 30 numbers, these 5 numbers 33577, they will occur with equal frequency. Okay, they will occur with equal frequency. Treat them as different numbers. So this 5 will occur 6 times, that is 30 divided by these 5 numbers. So it will occur 6 times since, sorry. So this number 5 will occur 6 times. That is 30 divided by 5 numbers, not the number 5. And then 3 and 7, since they are occurring twice, they will occur 12 times. Okay. 3 and 7 will occur 12 times. So sum of the digits at unit places which we were taking, it will be different. This 5 will occur 6 times, and this 3 and 7, they will occur 12 times, 12 times both of them. So the sum will become 150. Sum will become 150, and the sum of the numbers, by applying the previous formula, it is going to be 150 into again 10 raised to 5 minus 1 upon 10 minus 1. So this is something which we had been dealing with. Then there are problems in other verses on finding number of 6-digit numbers out of given 9 digits and all that. And so these are few verses on this permutations and combinations. And lastly, a very hard problem is tackled by Bhaskaracharya, but of course not completely. In the last two verses, Bhaskaracharya is talking about partitioning of a number. Okay, Bhaskaracharya is talking about partitioning of a number. So what is meant by partition of a number? That given number n, in how many ways we can write it as sum of m natural numbers. Okay, so here we are going to write the number n as sum of m natural numbers. So for example, if we are going to write the number 7 as sum of two integers or two natural numbers, not in. So we can do it in 3 ways, that 1 plus 6, 2 plus 5, and 3 plus 4. But actually, when we are counting these partitions, for us the addition is commutative. So 6 plus 1 and 1 plus 6 is not different. But when we are counting these partitions, we count 6 plus 1 as different partition. Okay. We count 6 plus 1 as different partition, and that makes it 6 partition in all. Okay. That makes it 6 partitions in all. So in much similar way, we can have more numbers. The number of partitions that can be repeated for uh, 3 numbers. Again, you have several such things. 1 plus 1 plus 5, then you have 1 plus 1 plus 2 plus 3. Oh, here in the last place, I have made a mistake. So I will better correct it. So we are talking about 3 numbers. So I have to take 3 numbers. I had made a mistake of putting more numbers there. Yeah, so there can be several combinations, and there can be several. Oh, even here there is a slight mistake, but that's, I hope you can understand that. That what I mean by this is you have to take three numbers and add them to make it seven. And when it comes to seven, there are several partitions. And the formula given by Bhaskaracharya for these partitions is n minus 1 factorial divided by m factorial into m minus 1 factorial. Okay, m minus 1 factorial. This is what is the formula. And if we count this for 7, it turns out to be 60. It turns out to be 60 because we are having 6 factorial divided by 3 factorial into 2 factorial. So this is something which Bhaskaracharya tried to work out, but I think Bhaskaracharya himself knew the limits of this. Bhaskaracharya says in his verses that this n minus m has to be less than 9. Okay, his formula works when n minus m is less than 9, and the numbers which are there in Leelavati's problems, they are very small numbers. This problem is partitioning of a number is a very, very hard problem of mathematics, and it was tackled for centuries. Okay, so I don't think here Bhaskaracharya had that kind of grasp of the problem, because he is limiting his scope, which is generally not there in most of his work, to n minus m. Their difference has to be less than 9 so that the things can be verified. In fact, if you look at the example given in Bhaskaracharya in Leelavati, is that he works it out for 13, sum equal to 13, that is n equal to 13, and m equal to 5. Okay, he works it out for sum equal to 13 and m, that is the uh, number of natural numbers, to 5. So in that case also we get 495 different combinations. 495 different combinations, and here the sum of the here the sequence of the numbers in the sum is very, very important. Sequence of the numbers in the sum is very, very important, and that sequence, if you change the sequence, you get a different combination, and that is how it is counted. So this problem was tackled by Ramanujan. Okay, Ramanujan tried to prove a formula, but he couldn't exactly the rigorously, in the sense we do it nowadays mathematics. He couldn't prove it, but it was proved 50 years later, 50 years after him, and using the techniques unknown to him. This partition of the numbers is a very, very famous problem. It has hard mathematical problem, and Bhaskaracharya even tried to work that out. Okay, Bhaskaracharya even tried to work that out, though not completely. This is very important from the point of view that where did our mathematics reach? Where did our ancient mathematics reach before we embraced the Western mathematics? Before we embraced the Western mathematics, our mathematicians were conceiving hard problems, were trying to solve them. They were conceiving hard problems and they were trying to solve them, though in a very limited way. Bhaskaracharya could give the formula. I think it is very important that he tried a problem, he conceived that problem and tried to solve it. Okay, so this is the last part of Leelavati. This is the very last part of Leelavati. And the next are these three very funny shlokas. One first is a very funny one. So it literally means that I had put the Sanskrit text as it is. So it literally means that if your disciples start taking false pride in their knowledge, garva, garvita ganaka batu, if they start taking false pride in their knowledge, then ask them questions from Ankapash. Okay, don't ask them the questions from multiplication, division, or squares or cubes, but ask them questions from Ankapash that will really kill their false pride. This is a very funny verse from Leelavati, has nothing to do with maths, but it underlines the conceptual difficulty in understanding the last part, that is Ankapash or Ganit Pash. I think that whatever was true in Bhaskaracharya's days is also true now. I think our students too struggle with permutations and combinations and those probability uh, problems when they are introduced to it. Only after good amount of practice they are able to do them uh, accurately without any mistake. So this last 259th verse, it says no, that for false pride, for your disciples taking false pride, ask them a question from Ankapash. Okay. Then this verse 260, it is the Leelavati, it describes Leelavati, but the way it has described, it says that this Leelavati, who has lots of good good vices, okay, she's she has very sweet voice. She knows, she has uh, a very good knowledge and all that. And this Leelavati, she if she becomes wife of anyone, that person will live in prosperity. That's what it says. Literal translation, I'm not going to do that. That is not my expertise. Maybe we have to ask Mrs. Khatri for this. But this shlok says that this Leelavati, who is with very good knowledge and lots of other good things, if she becomes wife of someone, that someone will always prosper. Okay, that someone will always progress. That person will do well. So here, really, this meaning of becoming wife, I think it should be taken in a very different sense, progress. And then the last, very last verse of Leelavati, it is about Bhaskaracharya. Okay. Again, this verse I have put it as it is in Sanskrit. So this Bhaskaracharya, he knew 8 grammars. I don't know in what sense it is said. This is somewhat very crude translation. So Bhaskaracharya knew 8 grammars, 6 medical books, 6 law books. I don't think law may not be a correct word here. What it reads from the verse is Nyaya Shastra. Okay. 6 Nyaya Shastra, 5 maths books, 4 Vedas, 5 Bharat Shastra, and 2 Mimamsa books. Okay. So Bhaskaracharya was well versed in all other fields. That is what it appears. Okay. Apart from mathematics, he was well versed in all other fields, and he was a religious person. That religious in the sense, he's saying that uh, that is this last two lines of this verse, that Bhaskaracharya, and he calls himself Kavi Bhaskara. Okay, he was a poet as well. So this Leelavati is a nice poetry explaining maths and its examples, and it is a very useful textbook on mathematics. In fact, here I will like to mention one thing, that in Leelavati, in first few verses, as I said, Leelavati is referred as small girl and all that, but verse 196 refers to methods from Leelavati. Okay, it refers to methods from Leelavati. So Leelavati for Bhaskaracharya was a book, but it was so he was so involved in that book that he used to treat this as his daughter. Okay, he used to treat this probably as his daughter. That this book was very dear to him, and he used to treat this as his daughter. That's why this name Leelavati and this initial references to small girl Leelavati has come. Maybe when he was calling it small girl, the Leelavati was he was writing the beginning part of Leelavati, so the book was itself very small at that time. And as it grew, it became full text on mathematics. So I think I will like to stop here. I will like to thank the organizers for giving me this opportunity to present something on Leelavati. I had made some mistakes in the presentation. Some typos still remain. I will correct the typos and share the presentation with you people. This is a very unique. I had been teaching maths in the university for very long, but this kind of presentation is a very unique thing for me. I am doing it for the first time. All other people in this workshop, they are really veterans in this field, but I thank the organizers for giving a novice to this field like me this opportunity, and I hope I have given some justice to the topics covered. So I think now we can take the questions if there are any.
Yes, Professor Sriram wants to ask.
Uh,
Yes, sir, please.
Oh, okay. I should say
Good
that
morning.
I attended nearly 80-90% of your talks, both are together. So it's really good. You presented very well. You're a mathematician, who is into history of mathematics. I'm a theoretical physicist, of course,
I know.
uh,
I have read
retired,
your book, sir.
retired some time back. So it was good. I just want to make one or two remarks.
Yeah.
Okay, so it's very good that Leelavati was presented well. Leelavati was a very good text. So she has covered many topics in Leelavati, actually very, very well. Okay. So now the Leelavati tradition was carried forward, in 14th century by a person called Narayana Pandita. Okay.
Yeah.
So
Yeah.
in fact, there's one Ganita Kaumudi. I think participants should know the Ganita Kaumudi is a very, some kind of an advanced text which will carries forward this Leelavati kind of topics much further. See, for instance, Madam was telling about the sum of sums, Sankalita Aikyam, Sankalita, and all that.
Yeah.
He will go into orth sum, sum of sums. Okay, he gives a formula for that, Narayana Pandita, which is useful, which is used in infinite series for sine and cosine later in Kerala. And
Yeah. In
in
fact,
yeah,
your work on that part also I am studying now.
yeah, good,
But,
yeah,
yeah.
yeah.
Because
The,
see, this is in Sanskrit. In Sanskrit, whatever
mm,
was there, yeah. But in Malayalam, this infinity was tackled very well. I mean, the
yeah, yeah,
series
yeah,
equations and all came out. So
Yeah.
it is unfortunate that we stopped there and then that Western mathematics came.
So this, and he, you see, amazingly, Narayana Pandita, in Ganita Kaumudi is written in Sanskrit. See, fortunately, it is available in, the Ganita Bharati. Ganita Bharati, many issues. There's one Paramananda Singh who has translated all the chapters of Ganita Bharati, this in Ganita Kaumudi. So that is good. See, in the sum of sums, he talks about, he gives a cow problem, very interesting, famous cow problem. There is one cow. And sorry, the Professor Gauri Shankar, am I taking too much time?
No,
No,
we
there is nothing fine, sir.
No, sir, we have so much time.
Okay, yeah. See, he says there's one cow, okay? So then for the next 20 years, it will give birth to calves. Let us assume that they're all female calves, okay? And each calf, you see, will start producing its own calves after 3 years. After it is 3 years old, it gives. Then what is the number of cows and calves at the end of 20 years? So all the sum of sums, etc., even 17th sum will come into the picture. And that is discussed in Narayana Pandita's Ganita Kaumudi. Is very good in Anka Pasha, in algebra, multinomial theorem, I think. So that so I hope somebody will talk about this later in some other workshop. Okay. Thanks a lot. It's a very good presentation, madam. I think you should give more lectures on more topics.
Yeah, actually, I will like to just say something here that I used to read. I mean, I am not saying that the kind of work which Professor Dani or Professor Sriram are doing, I haven't done that kind of work, but I used to read about this a lot. And I used to have this very uncomfortable feeling of not reading the original text. Okay. So once I had a chance to work with Sanskrit scholars. This Sanskrit scholar, Maha Mahopadhyay Devdatta Patil, he wanted to do Leelavati and Bijaganet. He was inspired by Professor Abhyankar. And he wanted a maths person as a part of his group. So I jumped at the opportunity and I went through Leelavati and Bijaganet. And it has given me a very good comfort level with those books. Okay. And this, I'm aware of the book mentioned by Professor Sriram, that is this Narayan Pandit's book. Also Ganesh Daivadnyastika Buddhi Vilasini and lots of other books which had taken it ahead. But maybe when I become more comfortable with that, I can explore that. But this Leelavati and Bijaganet, I actually sat with Sanskrit scholars and did it like them. So that level of comfort, I feel very good now. That's the reason why I had chosen Leelavati.
Yeah, that's good. That's great. Yeah, good. Yeah.
Hello. Are there any questions from audience? I think Professor Katre sir is here. Would you like to remark something, sir?
No, only about the partitions thing. Ramanujan had given a formula, Ramanujan and Hardy. Yeah, they had given a formula, which is a series formula. And, it was later on made better by Rademacher. So it is called Ramanujan, Hardy, Rademacher infinite series. So that also there is why Rademacher could modify that formula made by Hardy and Ramanujan great personality. That itself was a question. But then I attended one conference in 1987 on the occasion of Ramanujan's birth centenary. So at that time, people pointed out or commented that Hardy was the culprit to give a sort of not so good formula. Because in the Ramanujan's letter to Hardy, first one, Ramanujan has given an approximation to the formula that they proved later. And that approximate formula should have been used to arrive at the series expansion. Whereas Hardy did not like that formula somehow, and for example, instead of sine, he wrote cos there, and therefore the formula which they arrived at was not so good. And then Rademacher started with the right initial approximation. Many times we know when we do a problem, even in numerical analysis, if your initial approximation is good, then you arrive at the result very fast. So something like that happened, and then Ramanujan's formula. Of course, same methods were used by Rademacher, and just improving the initial approximation, which was already hinted. I mean, it was already there in the letter of Ramanujan to Hardy. He used that, and he was able to get the correct formula. So this partition thing is a very interesting problem, and it is interesting to know that Bhaskaracharya also tried to solve this partition problem, because the number of partitions of n becomes very large uh, soon. Means even for small values of n, the value of Pn is very large. So that's why it's a very difficult to get a good formula for that. But it is interesting to know that Bhaskaracharya actually tried this one. Thank
Yeah,
you.
that is where I found the intellect of Bhaskaracharya, that he tried to solve such a hard problem.
Yeah.
In posing this problem and tried to solve this, that itself is a great.
Ah,
And especially, see, we have always taken calculators and computers for granted. Okay, even for our generation, the calculators were easily available since our college days at least. But in those days, this partitioning, how would they test even for smaller numbers? Can you imagine that? In fact, all these people who are here in the workshop should try to imagine in what context, in what conditions this mathematical development took place.
yeah.
Okay. Yeah.
Also, this sum of sums that appears also, for example, if you count laddus in a heap of laddus. For
Yeah.
example, if you have one laddu at the top, below that laddu, we should have three laddus. So that is 1 plus 2 actually. Then
Yeah.
below those three laddus, there should be six laddus, on top of which these three are placed. So that 6 means 1 plus 2 plus 3 actually. And below that, there are 1 plus 2 plus 3 plus 4, that is 10. So the number of laddus in that heap is going to be the sum of sums in some sense. 1,
Yeah.
1 is 2,
This
1
is
plus 2
great.
is 3, and so on. So that way, this problem, probably they might have solved this problem to find out the number of laddus in a heap. And
This
that's
is
how,
a Leelavati type of example. Yeah.
yeah, yes. Leelavathi's example. And it was also there, this problem is also there in Aryabhata. Aryabhata also has solved this problem and given the formula for sum of sums, as you have mentioned. And of course, Bhaskara already mentions that various things which are there already in the earlier textbooks he has taken together, and of course, many new things also he has thought about and put into it. So, all these things, some new things and some old things are there in the work of Bhaskaracharya. Thank you. Yeah.
Oh, okay, thank you, sir.
Yeah.
Madam, some participants are asking for PPTs. If
The PPTs I'll share with you, and then we
yes,
can.
I will request all the speakers, if possible, they can share their PPTs so that it can be provided to the participants.
PPTs I'll share with you. There, I mean, I'll check the PPTs rigorously for typos,
Yes, 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 yes.
and
And one
then
more thing,
I'll share.
yes, one more thing I would like to point out here. If you people can share the references where these contents the participants can,
Yeah, yeah, sure, sure.
uh, whether these things are available on Amazon or any platform, so that those who are interested they can purchase all these contents. If there is any information, please share with participants.
Yeah, yeah, sure, sure.
Okay, so now, so we are towards the end of this talk. So would like to thank Professor Smita Wadekar, madam, for giving us time in this workshop, and she has presented two very beautiful talks on these topics. And I hope that participants are certainly benefited with these two talks, and they will work in this direction. They will search the literature and work on these topics, because Indian mathematics has a lot of things which we have to study. So with these words, I would like to thank Madam for those these two talks, and in future certainly we will try to have some more talks if possible in physical mode. So thank you once again, Madam.
Okay. Thanks a lot. Thanks for inviting me.
Thank you.
Yeah.
Thank you.
And
Now we will
especially
have-
thanks to Professor Katre, because of whom these lectures happen.
So now we will have a 20 minutes break, and next talk will be at 12:20, and Professor Katre will continue from where he left yesterday. So he will start at 12:20. So be connected, or you can join 5 minutes before, means 12:15, so that we can start the lecture on time. Okay, then thank you.